So now we're gonna check LP sequence. So in the previous video we discussed sequences, and the special property about LP sequences is, suppose we have a sequence space where every point is an infinite sequence. So say if capital X is a point, it consists of x1, x2, x3 dot 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 till x infinity, and we say that this vector is in LP space when this condition holds, which is this, that if you take the pth power of the modulus of each of these elements and sum them, that sum should be less than infinity. So we see that it is a Banach space. So LP space is a Banach space with respect to the norm. So this norm induces a metric. Let me write. So if this is a point X, okay, this is the norm of a single element capital X in my LP space. Now let us take another element, which is another infinite sequence Y, and let me write Y as something like, okay, y1, y2 dot 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 dot. And then if I take the metric between x and y, so should rather write it at capital X and capital Y because these are the points. So capital X is an infinite sequence, capital Y is an infinite sequence, and the metric between them is given by this formula. So you have summation of I ranging from 1 to infinity. Then you have modulus of xi minus yi. Maybe I should use another pen. Minus yi to the power p whole to the power 1 by p. So this is how you define a metric in our LP space. And when I say it is a Banach space, I mean that corresponding to this metric, the Cauchy sequences converge. And now we talk about L2 space, which is a Hilbert space with respect to the inner product. So again, we see that L square is a Hilbert space with respect to the inner product. This is the inner product. You have to remember, if you can't see it clearly, that this is complex conjugate of y. It's not just y, it's the complex conjugate. We take complex conjugate again because one of the properties has to hold true of inner product, that the inner product of x comma y is equals to the complex conjugate of inner product of y and x. So I can write it like this. So the reason why it's a complex conjugate is that we had seen before that this was a property that the inner product of x and y is equal to the inner product of y and x complex conjugate. So now we are talking about the space big LP. I cannot stress enough how much this space matters. So the big LP space is the space of all p integrable functions. So if you see before, what we did were in small LP, this sequence to the power of p. So the individual elements of the sequence, you take the mod of them, you raise them to the power of p, and then you add up all of them. This was less than infinity. And similarly in big LP spaces, now every point in big LP space is a function. And the property of this function f is that if you take the modulus of it, integrate it over omega, so omega is a subset of Rn. Okay, and if you integrate over omega, then it should be less than infinity. If my f satisfies this property, then this f is in big LP. Omega is important. So omega is the range of integration, and my functions belonging to big LP space satisfy this property. And again, my big LP space is also a Banach space with respect to this norm, and my big L2 omega is a Hilbert space with respect to this inner product. We've seen in the previous videos that how inner product induces the norm and then it induces the metric, and that's why the Cauchy sequence converges to a limit which lies in the same set. And one more thing I want you to take notice of is that this is the inner product. Even in big LP space, this is the complex conjugate of G. Complex conjugate. This is to, again, when we defined inner product, we defined 4 properties. Out of that, one property was inner product of x, y was equal to inner product of yx. In order to satisfy this property, I have to take the complex conjugate of my function g. Now we return to another class. We talk about the set of all bounded functions, which are denoted by b omega. And when I say bounded functions, so this is how I specify my norm in p omega space. So close your eyes and imagine a space of all bounded functions. So the set p omega is the set of all bounded functions from omega to c, and this is also a Banach space with respect to the supremum norm. So this is how I define my norm of an element in my Banach space, and this is assigned like this. So you have your x belonging to the set omega, and then you calculate f of x, take the mod of it, and the supremum value is assigned as the norm of the operator. Norm. And now we look at 2 special cases. So let omega be a non-empty closed subset of Rn. And then we say that Cb omega is the space of all bounded continuous functions. This continuous is very important and beautiful here. And as we have seen in the previous videos, the way I define continuity, I see that again my space Cb omega, which is the space of all bounded continuous function, is itself a Banach space. Banach space meaning if I have any Cauchy sequence, this is how I write a sequence with the curly brackets, by the way. And if I take the limit n tending to infinity, xn, and whatever x I get, this x also belongs to the space, say, Cp omega. When this is the case, then I say that, okay, the limit lies in my space itself, so it's a Banach space, and this is the norm. The way I define norm in the case of b omega, which was the space of all bounded functions, and this is called supremum norm. So when I write infinity as a subscript, I mean the supremum norm. So supremum norm is defined like this. You feed your operator with values of x from your set omega, take the maximum value, you take the maximum value after that, or should I say supremum. One of the things that I would like to clarify about supremum and maximum is, suppose I have a sequence 1 by n, and it's defined over the set in case 1 to 0. So now when I say that the limit n tending to infinity is equals to 0, then I say that 0 is the minimum value of my sequence. Okay. Now suppose I change the space in which we were operating. Rather than this, I change it from 1 to 0 open. Now when I do limit, or let me use a different pen. So we would see that now when I do the same operation, that is limit n tending to infinity 1 by n, then 0 is not the minimum value, rather it's the infimum value. Because if 0 does not lie in the set, then the value of 1 by n would approach 0, but it itself would never be 0 because 0 is not a part of my set. So I say that 0 is the infimum value of the sequence. And the same logic is, so we saw that 0 is the minimum value when 0 was part of the set that we were operating in. And when 0 is not a part of the set on which the sequence is defined, then 0 is the infimum value. The same logic holds with supremum and maximum. If your limit point lies in the set, then you call it maximum. If it does not lie, then you call it supremum. Again, so we were talking about the set CB omega of all bounded continuous functions, and we say that this is also a Banach space with respect to this norm, in the supremum norm. And we know that the space of all bounded continuous functions is a closed subset. The space of all bounded continuous functions is a closed subset of p omega, or the space of all bounded functions, which makes sense to me. So if I have just bounded functions, and now I have a special quality attached to them, which is bounded continuous. Bounded plus continuous. So of course you can see that this class should be a subset of the space of all bounded functions, and we know that every continuous function on a closed bounded set is bounded. On a closed bounded set is bounded, and therefore in this case CB omega is equals to C omega